The packet queue buffering system is a middleware layer responsible for incoming network datagram management. This document covers system architecture, buffer allocation semantics, and overflow handling procedures. The queue operates independently of transport protocol specifics. Buffer slots maintain fixed size allocation. This manual assumes familiarity with circular queue fundamentals and basic network terminology. Refer to previous documentation for prerequisite concepts. Queue initialization occurs at system startup or upon explicit reset invocation. The allocator reserves contiguous memory pages according to configured capacity. Default capacity is set to 16,496 byte slots. Alignment requirements mandate buffer start addresses at cache line boundaries. The head and tail pointers initialize to position 0. Watermark thresholds define congestion boundaries and are established during initialization phase. In queue operations, insert incoming packets at the current tail position. The operation acquires a spin lock protecting queue state. If tail pointer equals head pointer, the queue is full and the operation returns an overflow status code. Otherwise, the packet payload is copied into the reserved buffer slot. Metadata fields including timestamp and frame length are written to adjacent control structures. The tail pointer increments modulo the total slot count. DECU operations retrieve packets in FIFO order starting from the head position. The operation acquires the same spin lock as in queue. If head pointer equals tail pointer, the queue is empty and the operation returns a no packet status code. The packet at the head slot is copied into caller-supplied memory. The head pointer increments modulo the slot count. Metadata is similarly retrieved and returned to the caller. Watermark management divides queue occupancy into 3 distinct operational regions. The low watermark is set to 30% of capacity by default. The high watermark is set to 80% capacity. When occupancy falls below low watermark, back pressure signals are withdrawn from upstream. When occupancy exceeds high watermark, back pressure signals are transmitted upstream immediately. Overflow behavior depends on the configured overflow handling mode. The discard mode immediately releases new packets when buffer capacity is exhausted. The tail drop mode discards the oldest queued packet when new packet arrival occurs at full capacity. The random drop mode probabilistically selects a queued packet for discard. The default mode is tail drop. All discarded packets increment the overflow counter for monitoring purposes. Binlock acquisition uses compare and swap atomic operations on a single byte guard variable. The lock value 0 indicates unlocked state. The lock value 1 indicates locked state. Contending threads execute exponential backoff spin loops before attempting retry. Maximum backoff duration is bounded to prevent indefinite CPU waste. Lock holders release the guard by writing 0 and issuing a memory fence instruction. Performance monitoring is implemented through event counters updated atomically. Total packets in queued counter increments on successful in-queue operations. Total packets dequeued counter increments on successful dequeue operations. Total packets discarded counter increments when overflow discard occurs. Peak occupancy counter tracks maximum simultaneous queued packets. Watermark cross encounters track transitions between operational regions. Timestamp recording occurs at packet insertion time using monotonic clock sources. The timestamp field occupies 8 bytes in the metadata region. Timestamp values are stored in nanosecond units since system boot. These values enable latency measurement and temporal ordering verification downstream. Timestamp overflow does not occur for approximately 500 years of continuous operation. Memory protection mechanisms ensure buffer isolation from unrelated allocations. The allocator requests dedicated memory regions from the operating system kernel. Guard pages are placed at buffer boundaries to detect out-of-bounds access. Read-only flags protect metadata control structures from accidental corruption. The kernel page table maps these regions with explicit access control attributes. Concurrent access patterns are supported through careful lock placement and atomic updates. Read-only statistics queries do not require spinlock acquisition. The current occupancy counter is updated atomically without spinlock protection. Multiple in-queue and dequeue threads may contend for the same lock. Lock contention metrics are recorded for performance analysis and tuning guidance. Recovery procedures address partial buffer corruption through several mechanisms. A CRC32 checksum is computed over each packet payload at in-queue time. On dequeue, the checksum is verified and packet is discarded if mismatch occurs. The queue state itself is protected by a separate integrity marker. If integrity marker fails validation, the queue enters a safe shutdown state and awaits administrative reset. Configuration parameters are loaded from a static configuration file at startup. The parameter file specifies capacity and number of buffer slots. The parameter file specifies buffer slot size in bytes. Watermark percentages are configurable with valid range from 10 to 90%. Overflow handling mode is specified as one of 3 enumerated values. Invalid parameters cause system initialization failure with logged error codes. Integration with upstream components occurs through a callback interface. Upstream components register their backpressure handler function during initialization. When high watermark is crossed, the registered callback is invoked with backpressure signal active. When low watermark is crossed, the registered callback is invoked with backpressure signal inactive. Callback functions execute synchronously within the DEQ code path. Testing procedures validate queue behavior under various workload patterns. Unit tests verify in queue and DEQ operations with empty, partial, and full queue states. Stress tests exercise high-frequency concurrent access from multiple threads. Overflow tests inject packets at maximum rate to validate discard behavior. Memory tests check for leaks and corruption using instrumented allotators. This concludes the packet queue buffering system documentation. The system provides reliable in-order packet delivery with configurable overflow handling. Performance characteristics remain deterministic across expected workload ranges. Monitoring metrics enable observation and diagnosis of queue behavior. Refer to the configuration guide for deployment-specific tuning recommendations. Support for extended features is available through supplementary technical bulletins.